Hello and welcome back to the Inside Java podcast, a podcast that discusses Java from Ember to ZGC, brought to you by the team at Oracle that builds Java. My name is Delabassee, and I recently had a conversation with Maurizio, Cimadamore, and Jorn Vernee about Panama Foreign Support. We decided to split this discussion in two episodes. So this is the first one, episode 9, where we introduce Project Panama's foreign support. And we then discuss in details the Foreign Memory Access API. So make sure to also listen the follow-up episode 10, where we continue the discussion and we discuss the Foreign Linker API in details. And now enjoy the episode. Maurizio, Jorn, welcome. Can you please first introduce yourself?
Hi, David. Thank you for having me on this podcast. I'm Mauricio, and I work for the Language and Tools team at Oracle. This team is internally known as the Lang Tools team. And historically, I'm more of a language guy, even if today I'm going to talk about Panama. And I have helped designing and implement some of the language features that we use every day, such as lambda expression or local variable type inference. And over the last couple of years, I started to work more on the runtime, and that's why I'm here talking about Panama today.
Okay. What about you, Jorn?
Hi, my name is Jorn Vernee, and since joining Oracle last year, I've been working on Project Panama, but even some time before that, outside of Oracle voluntarily through OpenJDK. And I've mostly been working on the Foreign Linker API. Since I joined, I've rewritten the entire backend and have been working on intrinsifying some of the support in there. And then on the side, I've also helped out with Project Scala, which is the transition to Git and GitHub.
Okay, so you were already contributing to Panama before joining Oracle. Nice. What about you, Maurizio? How did you end up working on Panama?
So it's a long story in the sense that after you work on type inference and deep type system issues for a long time, you kind of develop a little bit of a tunnel vision, I guess. So I wanted to expand a little bit my horizon and work on the core platform a little more. And so I ended up first helping out with Valhalla. So I helped developing some of the support for minimal value type, which was one of the proposals that we have a couple of years ago. And then from there, since I had a lot of fun, I continue on that path and I started working on Panama and help out there.
Okay. We need to start by clarifying something, as today we will discuss Project Panama, but there are really two angles to Panama, two facets. One is foreign function support that we will discuss today, and the other one is the vector API. So whenever we say Panama in this episode, we really mean Panama's foreign function support. And by the way, if you want to learn more about the second facet of Panama, you should listen to episode 7, where we discuss the vector API with John Rose and Paul Sandoz. Okay. Now back to Panama's foreign function support. The first things that I'd like to ask is, what are we trying to solve with Panama's foreign function support?
So that's a very good question. I guess we start from a little bit of a reality check in the sense that not all the libraries out there that developers want to use are written in Java. For example, TensorFlow, BLAST for linear algebra, OpenGL for graphic processing. They are all libraries that are written in C or C++. That means that there is no official Java port for this library available. And if users want to use those libraries, they have to be able to reach those libraries in some way. Java today has a way to interop with those libraries, and that is called JNI, Java Native Interface. JNI is I guess you can call it a pretty general mechanism for calling into native code, but it comes with a lot of obstacles for the developers. One of these obstacles is that you have to declare these so-called native methods in the Java source code, and then you have to do a pre-processing step where from the native methods, basically a tool, which used to be Java H in the past and now is Java C, will generate a bunch of header files. This header file will contain some signature for the native function that you need to implement, and that means that the Java developer will now have to develop some C or C++ code to write the implementation for these functions. Then it will have to compile those functions using GCC or Clang or whatever platform compiler is available on the particular platform. And at the end, the user will come up with some shared library the shared library will be linked in the JVM. And that's basically what allows the VM to call into a native method. So it's a very convoluted process. There are a lot of things that can go wrong. But I would like to kind of draw attention on 2 points. The first is that JNI is kind of perceived as being a little bit inefficient, and maybe Jorn will give us a little bit more insight on that later. I think that's a false claim. For that reason, people tend to pack a lot of functionalities inside of a single JNI call because they want to avoid the overhead for transitioning repeatedly from Java to native and back. So these native methods that start off quite simple, they end up being quite convoluted. They do a lot of argument validation and things like that. The second fact is that since this code is completely opaque to the JVM because it's all native code, the JVM has no opportunity to optimize all the code that is inside this JNI method. So if you write in JNI anything that is more than just a trampoline to some foreign function, you may end up with code that is actually slower than if you wrote that code in Java. So with Panama, we're trying to address both of these concerns by allowing developer to express a 100% Java solution for calling into foreign function. And that will hopefully allow the JVM to better optimize and more efficiently handle calls into native code. Just to give you a little bit of an example, the TensorFlow API, at least the earlier iteration of the Java TensorFlow port, contain roughly half native code and half Java code in there. And that was due to all the massive amount of JNI code that was available in there. As a matter of fact, in the recent version, all this native code has been swapped out and replaced by using a framework that is called Java CPP. Java CPP is a framework that has been developed by Samuel Odette and allows people essentially to bypass a lot of these oops and obstacles that are typically associated with writing JNI code. So as you can see, the community have already resorted to a lot of different mechanisms to avoid the pain of using JNI. And Panama is trying to solve this problem at the root by offering a supported approach that is well optimized within the JVM and runtime ecosystem.
Okay. Before we talk about the different APIs, why that name, Panama?
Well, Panama is obviously a very important geographical place. Not only its isthmus connects two continents, because it basically connects the Northern American continent with the Southern American, but it also serves as a transition with this channel from the Pacific Ocean to the Atlantic Ocean. And it's been used over the last 100 years, and it helped ships avoiding a lot of dangerous trips all around the southern tip of the Americas, and to travel more safely from one side to the other of the planet. And so we think it's a very apt name for the technology that we're about to introduce.
Yeah, indeed. Now let's talk about Panama itself. Can you, in a nutshell, describe its architecture?
So that's a good question. I'd like to take a step back because I guess a couple of years ago, there wasn't as much in terms of architecture when it came to Panama. The main building block which Panama was essentially structured was the tool that was called JExtract. This tool was a tool that was able to process native headers and to generate a Java interface that then developers could use in order to interact with the native library. While going down this path, we realized that, yes, this approach was good, but we were missing some opportunities for solving other problems along the way. One of those problems is, for example, plain access to off-heap memory. A lot of frameworks need to do off-heap access. And if our approach is completely focused on, for example, having an API for mimicking C pointers, we kind of give up some of the use cases that are there in the more pure off-heap access case. Secondly, we realized that a lot of the work that we were doing in order to support foreign function call was really centered around the idea of modeling native function call as method handles. So armed with those two new pieces of knowledge, we were able to basically come up with a new Panama architecture that was composed of several layers. At the bottom layer, we have the so-called foreign memory access API. You can think of it as a replacement for the byte buffer API that has a little bit more focus. It's a little bit more directed towards solving some of the off-heap memory access use cases. The second layer is the foreign linker API, which, as I said before, allows you to link a foreign function using a Java method handle. And then on top of these two layers, we have a tooling layer. So we still have JStruct, but now it's a JStruct that is defined on top of the former layers, which essentially generates all these building blocks, so var-handle, method handles that are necessary in order for you to interoperate with a certain native library.
Okay. Now, the foreign memory API is really at the core. What I mean is that the foreign linker API is leveraging the foreign memory API. Is that correct?
Yes, in the sense you need to be able to access memory before you can even speak about calling a native function. Because, for example, if a native function takes, for example, a struct, how is the Java code supposed to allocate the struct? How is the Java code supposed to set fields or get fields inside the struct? So that's why the memory access API comes first. And that was a realization that came pretty late in the history of the project. And in hindsight, it was obvious, as all the things that when you work on these big complex projects. But I think it was a very helpful realization of that.
One of the key realizations here is that the old Panama prototype basically gave you one high-level API that you would have to interact with. So if there were existing frameworks like JNA, JNR, even Java CPP, they would have to write again on top of our high-level layer. And basically, this could create some inefficiencies because they had to go through our high-level layer. But by splitting out this lower-level foreign linker API, other frameworks can change their implementation to use this linker API directly as well. So we're not directly competing with existing frameworks anymore. We're just providing an alternative extraction tool with JExtract.
Okay. So let's zoom a little bit on the foreign memory access API. So what issue does this API solve? And also, how does it compare against the byte buffer API?
The foreign memory access API starts from the fact that off-heap memory for many frameworks out there is a fact of life. If you look at Netty or Lucene, these frameworks basically all rely on being able to allocate memory off-heap. Sometimes it's because they want to avoid the cost related to garbage collection. Other times it's just because they want to be able to pass memory more easily to native libraries. But in all those cases, you need a way to allocate memory off-heap and also to dereference this memory. The byte buffer API has always been the way to go in the Java SE API. It's the only supported API that allows you to allocate a chunk of memory off-heap. There is, of course, the unsafe API, but the unsafe API is not really an API. It's not even accessible by default unless you tinker a little bit with the platform. The byte buffer API, unfortunately, has two main limitations. First, the indexing system used by the byte buffer API is based on int instead of long, and that means that your addressing space is rather limited. While that was an acceptable limitation in 2002 when the API was designed, you can understand that now with persistent non-volatile memory and things like that, this is starting to become a little bit more of a problem, where people want to map very big chunk of memory. So having this limitation of 32 bits in indexing scheme starts to become more of an issue. The second limitation is that byte buffer never offered an explicit way to do memory deallocation. What that means is that byte buffer only releases memory when the garbage collector is able to prove that the byte buffer instance is no longer around. So basically, you are at the mercy of the garbage collector when it comes to deallocating memory. The problem here is a little bit subtle. Since the byte buffer instance is very small to the garbage collector will never really feel a lot of pressure to go and free this byte buffer instance. The problem is that this byte buffer instance, which is very small in the heap, is in reality very large because it may cover a large region of memory of heap, but the garbage collector doesn't see it. So you may wait for a long time before the memory is actually collected. So what we tried to do with the Memory Access API was to solve both of these problems by offering a more modern, long-based indexing scheme, and also by providing an explicit way to deallocate memory once users are done operating on said memory.
I think it's worth answering the question, well, why can't we just add explicit deallocation to the existing byte buffer API, which has been requested many times as well as a feature enhancement? And the problem is basically that at the time there was no way to make this safe in a concurrent environment, where you could have one thread trying to close the byte buffer, which would clean up all the memory, and another thread at the same time trying to access the memory. If the memory gets freed while the access is occurring, and maybe it gets even assigned to someone else, you might be corrupting memory if you're doing a write, or you might be hitting an OS memory page that is now locked and you will crash the VM. So there is no way to make that safe. But we found some solutions to the problem while starting from scratch with deterministic deallocation in mind.
Okay, we'll come back to the deallocation question later, as I think we haven't fully set the stage yet. So I'd like to spend a few minutes on the main concept, the main abstraction of the Foreign Memory Access API.
Yeah, the Foreign Memory Access API has a main abstraction that is called memory segment. So a memory segment basically models a contiguous region of memory that has some bounds. There are many kinds of bounds that a memory segment has. So there is a spatial bound. So a memory segment has a start and a finish. So you can only add the reference memory within those bounds. Then there is also a kind of life cycle bound, if you want to call it that way. So a memory segment may be alive or may be already free. And you can only access a memory segment if it's alive, of course. Otherwise, you, as Jorn mentioned before, you can end up accessing memory that is no longer there, so you may crash the VM, or you can even corrupt memory. The third kind of bound is a thread confinement bound. So memory segments are born with confinement in mind. So when you create a memory segment, it's associated to the thread that created that particular segment. And then there is an API to remove ownership or to change it on the fly according to the need of the API. And together, all these different bounds provide safety when dereferencing memory. One thing that is different from the byte buffer API is that in the byte buffer API and in many actually memory related APIs, you have a lot of methods to do memory dereference operation. So you will see a lot of methods such as getInt, putInt, getFloat, putFloat, and things like that. The memory segment API doesn't provide any of that. Instead, it basically doubles down on an existing API that was introduced in Java 9 called varhandle. So instead of giving you ability to dereference memory segment directly, the API allows you to produce a varhandle that allows you to then dereference the memory segment. And by doing this decoupling, we are able to provide a much richer dereference API, which supports all the carriers that people want to operate with, but also support atomic access, memory fencing, and things that the byte buffer API cannot simply support.
Yeah, to give an example for that, let's say that you have a byte buffer that actually represents a two-dimensional array, and you want to access it by passing an X index and a Y index to get to one of the elements. Well, theoretically, we could add another method to byte buffer that takes two indexes and actually also takes a scale for the first index to access one of these elements. But what if we want to do 3 indexes? What if we want to do 4 indexes? What if we want to do, I don't know, every second element? This becomes an explosion of extra methods that would have to be added to byte buffer. But because var handles are basically polymorphic in their type, we can use one API, the var handle API, to do all these different kinds of accesses in just one API that is basically open-ended.
Yeah, indeed. The var handle API really makes sense here. And that's also a good segue to discuss memory layout.
Yes, memory layout is, I think, combined with varhandles, one of the superpower of the memory access API, because as Jorn said before, it's all good and well to be able to, get an int out of memory or set a float in memory. But the problem is when it comes to define complex data structures. And since we know that in Panama we want to be able to solve the problem of interoperating with foreign libraries, we definitely have to have a way to describe, for example, what is the layout of a struct. We have a point struct, like Jorn mentioned, it has an X and Y coordinate. How do we describe that layout? And the answer of the Memory Access API is to introduce a new API called Memory Layout, which allows developers essentially to just do that. So they can construct an object which represents the layout of a certain memory region. And then once we have that object, we can ask a lot of questions, such, for example, what is the offset for the Y coordinate inside a point? Or please give me a variable that allows me to set the Y coordinate of that point struct. Or what is the size of a point struct? So all this stuff can be computed just by using the layout API. So combining together the variable API plus the memory layout API gives us a very powerful tool in order to reason about structured access. And that is a very good power to have when it comes to interoperating with native libraries.
Okay, so that's memory layout. But can we go back to memory segment for a minute? So you said that memory segments are confined and that there's an API to deal with ownership. Can you elaborate?
Yes. So when you create a memory segment, the segment is associated with the thread that did the creation. That means that only that thread will have the ability to the reference memory within the segment. This is crucial in order to provide fast access performances and safety. Because if a memory segment is confined, of course, it's not possible for two threads to race when accessing the segment, or for one thread to access the segment while another thread is closed in the same segment, because, the segment is confined, so only one of them will have access to the segment. Of course, this situation is a little bit suboptimal. There are cases where, for example, when you want to share a segment with multiple threads, in which this restriction is a little bit too much. And so in the course of the numerous iterations that we had over this API, we tried to relax the restriction a little bit. So one of the first things that we introduced in the API was the ability to give ownership of a segment to a different thread. So if the owner thread knows that another thread is about to take over for accessing that segment, it can explicitly perform an ownership change on the segment and then give the segment to another thread. Of course, that requires the original thread to know which thread is about to take over when accessing the segment, and that may be again, too limiting. There are often cases, especially when dealing with foreign function calls, where we absolutely have no idea of what is the owner of a certain segment. So in order to cope a little bit with that, we recently introduced the ability to share a segment. When you share a segment, you're basically doing one thing, which is removing the thread ownership that is associated with the segment, which means that every thread is now able suddenly to access that memory segment and also to close that memory segment as well. You may ask, well, how can we do that efficiently? How can we allow threads to race into a segment without crashing into each other? Well, we managed with some black magic from the VM team. They helped us a lot in order to develop a scheme that allows us to access memory without any form of locks. So basically the performances of accessing memory in share segment is the same as performing access on confined segment, but share segment come with a price when it comes to the close operation. So closing a share segment is a more expensive operation than closing a confined segment. And that's because the VM has to make really sure that there is no other thread at that same time that is currently accessing that very segment. You can think about it as a stop the world pause, where the VM is inspecting all the threads and looking at who's accessing the segment. And if nobody's accessing the segment, then the segment will be closed.
Okay. So we just discussed thread confinement, but that's not all, as there are other bonds, such as special bonds and
the liveness check.
Liveness checks. Thank you. So those are necessary to enforce safety, but what is the cost of having all those checks?
Yeah, that's a very good question. And I know it's something that people are very concerned about. So the performance target for the memory access API has always been to kind of come as close as possible to plain and safe access. Of course, if you just measure the performance of a single memory access, that goal is not achievable because, as we said before, when you do a single memory access, you will have to check whether the segment is still alive, if the access is on bounds, and if the confinement thread is the same from where memory is being accessed. But the JVM gives us a special power, which is if you access memory within a very tight loop, then the JVM is able to apply some optimizations on that loop. And so it can realize that the memory being accessed is always the same segment. And so all the checks that will be applied on each access will be hoisted out of the loop. So they will only be performed once at the beginning of the loop, and they will not be performed on every access. So if you look at the assembly code that the JVM is able to emit while using the memory access API, you will see that there's no check at all. And in fact, in certain cases, the VM is even able to vectorize memory access on consecutive addresses. So basically, you get the same performances that you would otherwise get with unsafe, and you pay very little for the extra safety check that are introduced.
Okay, and now deallocation. So we briefly mentioned deallocation earlier. Can you give us a rapid overview of the two approaches, and maybe start with explicit deallocation?
As you said before, one of the main weaknesses of the byte buffer API is that there's no way for the user to say, well, I'm really done with this byte buffer and I want all the memory to be deallocated. In the memory access API, a memory segment actually has a close method that you can call to get rid of any foreign memory that can be associated with a particular segment. So of course, with power comes responsibility, which means that if you are no longer using a segment, you must remember to call the close method before the segment is basically goes out of scope, because at that point you will have a native memory leak. To help a little bit with that, the API for memory segment extends the auto-closable interface, which means you will be able, for example, to use memory segment inside a try with resource block, which means that the allocation and the close call will basically happen for free. But yes, in general, this is something that developers will have to be more conscious about when using this API.
But let's say that a developer doesn't want to or cannot take advantage of deterministic deallocation. Is there anything else he or she can do?
One option that we introduced in 16 is to still allow developers to attach a memory segment to a GC cleaner. So if a user, for example, is a little bit uncertain of whether a segment is still going to be used or not, they can essentially leave the decision of when to deallocate the foreign memory associated with a segment to the garbage collector, basically in the same way as it was done for byte buffer. Of course, as it happened for byte buffer, this will have a performance implication. So it is probably better to do this if you have a long-lived memory segment rather than if you have a short-lived one. But there are situations in which this may be helpful. And so we added this extra API point that allow you to register segments with a cleaner. So if people want not to use explicit deallocation and to use the cleaner instead, they can go that route if they're okay with the performance compromise.
Okay, thank you. We'll end the first episode here. We will continue and discuss the foreign linker API in the next episode. So make sure to listen to that episode.